now we're ready for part 4, which is on diffraction. So in our previous labs, we've learned what reflection and refraction are. So in the case of reflection, light comes in and then it bounces off of something. So that was called reflection. Then you had refraction, where light is coming in, but this time, instead of bouncing off, it's going through. So this down here, this could be like glass, and then this thing up here could be air, and then what would happen is that it's going to bend off in this direction. So that's going to be called refraction. But now what we want to look at is diffraction. And so in that picture there, we have a barrier. Okay, then the waves are coming in this direction, and then when they feel the barrier, they're going to turn. So diffraction is the bending of a wave as it goes around something. Now notice that these waves up here, they don't notice the barrier. So they just keep on going in a straight line. But these waves down here, when they encounter this edge here, they feel it and then they turn. And so that's going to be called diffraction. Now, if you could have two barriers. So we know that if you've got a barrier up here, that it's going to curve around it. What about if you had a barrier up here and it curves around it like that? Then what do you end up with? Well, then you end up with something like this. So you're going to have rings. And that's exactly what we saw when we had a single faucet that was dripping, that it produced rings that expanded like that. So that is essentially being caused by diffraction. Okay, now we're going to go back to the simulation and we're going to go to one slit. So we're going to our slits and we're going to set this to one slit. Over here we had it on two slits. Now we're going to set it to one slit. And now we got this. Okay, now we could do the faucet, we could do sound, or we could do light. So if we click on this, there's our water waves, and they are approaching a single slit, and you see that it's making the ripples. It's making those circle things. So it's diffracting as it goes around here, and it's diffracting as it goes around here. Now what I want you to notice is that there are going to be certain angles where it's extra bright. And you notice that it's extra bright along this line here. Now look right here, down here, and then up here, you see that it's extra dim. Now one of these is corresponding to constructive, and one of them is corresponding to destructive. So which one's which? You should know this already. And I want you to change the wavelength. So it might be better if we go to light. Okay, so there's light waves. And it's approaching a single slit. And it's easier to see in this picture here that it's extra bright here. And then look down here. Do you see it's extra dim? Okay, now I want you to change the wavelength. So you can do that by, this is the amplitude up here. And you can change the frequency with this slider. So change this slider here to different colors and observe that the angle where it gets dim changes when you do that. Then I also want you to change the slit width. So that's this part right here, and you can do that with this one. So this slider here is going to change the width of the slit. And again, I want you to notice it changes the angle where the destructive interference is occurring at. Now, let's go back to the lab here. So I'm going to let you answer these questions here, and now we're going to go down to this. So this is the equation that is going to tell you where the first destructive interference is going to occur at. Does that look familiar? So look at this formula here. You should have seen that before because it's very similar to this formula up here. So this one told you what angle would constructive interference occur at. This equation down here is going to tell you at what angle does destructive interference going to occur at. And in particular, it's the first destructive interference. Because do you see there's no n in front of the lambda over here? Actually there is, but we're only concerned with the first destructive interference, so n would be equal to 1. Notice it depends on the wavelength, and it depends on A, where A is now going to be the slit width. So it's a different letter A, in that formula there. Now if you're interested in this formula, which I know that you are, so if you're interested and you're saying to yourself, well, where did this formula come from? Well, you really need to take like a upper level physics class, but it's on the internet, so you can find some other guy lecturing about this, and he or she will show you where this formula comes from. All I want you to see is that there is a formula, and it depends on 3 things. So it's going to depend on the wavelength of sound, the wavelength of the light, the wavelength of the ripples if it's water. It's going to depend on the size of the slit, so that's going to be A, and then it's going to depend on the angle where the interference diffraction is going to occur at. So that's it. So now we're ready for our post-lab questions. So I want you to go through this. What's the purpose of the lab? What's the definition of interference? And then we've got 2 waves here that we're going to add together. And the question is, what kind of interference is that going to be? So that's going to be pretty easy. And then it says here, if they were light waves and they interfered with each other, what would you see with your eyes? So would it be extra what, or would it be extra what? Okay, number 4, how do noise canceling headphones work? So you've heard about these headphones that you can put on, and what it does is it eliminates outside noises so that you can listen to the music in your earphones. How do those work? Well, it has something to do with constructive and destructive interference. So you find on the internet an article where it explains how noise canceling headphones work, and then just summarize it down here. Okay, now we've got green light passes through 2 slits and is bent at a certain angle. Red light passes through the same 2 slits. Which one would bend more? Well, you can do this with your simulation, or you can do this using this formula. So you can also do it using this as well, because you're going to know what's happening to the wavelength, and you know what's happening to the slit. Now the slit is the same. Oh, it's a 2 slit. Sorry about that. So 2 slits, we would be using this formula up here. Now it's the same two slits, so the D isn't changing, but the wavelength is. So if this wavelength, let's say if this wavelength gets larger, what does this thing over here have to do in order to compensate? And our two colors are going to be green and red. Let's go back down here. Green and then red. You need to look up on the internet the wavelength of green and the wavelength of red. One of them is bigger than the other one. And so based on that, you should be able to figure out which one's going to have the larger angle. Then number 6, explain how you can hear someone outside of a door even though you can't see them. So the question is that let's pretend that here's a door, okay? The door's open. And then you are over here, so you're inside the room. But somebody is over here outside the room and they're saying something, but yet you can still hear it. You can't see them because the wall's in the way, but yet you can still hear them. Why? So it has something to do with what we've been talking about today. Then number 7, when light from a star goes down the barrel of a telescope, it can be diffracted. And so the question is, what would that do to the image of the star? So what we're talking about here is, here's a star, and then a telescope has a barrel like this, and then normally it's got a mirror in the back of it, and then the light from the star reflects off this mirror, and then it goes to a place where you got the lenses so that you can see the star. But because this is a tube, it's like a slit, so that when light from the star goes into this tube, it's going to be diffracted, just like light when it went through a single slit was diffracted. So the question is, what would that do to the image of the star, and would that be a good thing or would that be a bad thing? So again, you might want to look that one up on the internet. And so that's it. So that's our lab for today. I hope that you have enjoyed it, and so I will see you next time.